Modern paint peels within a decade. Exterior coatings blister and crack. Interior walls fade and chalk. Yet medieval frescoes painted directly onto wet plaster 700 years ago remain vivid and intact. The colors haven't faded. The surface hasn't flaked. Cathedral walls painted in 1300 look fresher than houses painted in 2010. This is the story of a pigment technology so sophisticated that modern chemistry struggles to replicate its permanence, and why every painted surface in your home is designed to fail. Chapter 1. The wall that sheds its skin. Stand in front of your house. Look closely at the painted siding. See the fine cracks spreading across the surface, the slight powdery residue when you touch it. That's chalk paint breaking down at the molecular level. The polymer binder degrading under UV exposure, leaving loose pigment particles. This degradation is irreversible and accelerating. Modern exterior paint lasts 5 to 10 years before requiring repainting. Premium paints might reach 12 to 15 years. After that, the coating has deteriorated too much to protect the substrate. The paint isn't just ugly, it's failing at its fundamental purpose, preventing water infiltration and material decay. The American Coatings Association estimates Americans spend $30 billion annually on exterior paint and related materials. That's not decorative updating, that's replacing protective coatings that have chemically failed. The entire painted housing stock of America requires repainting every 7 to 12 years to prevent building deterioration. Meanwhile, in the Basilica of San Francesco in Assisi, Italy, frescoes, painted by Giotto di Bondone, between 1297 and 1300 remain substantially intact. The colors ultramarine blue, vermilion red, yellow ochre, terre verte retain 70–80% of their original intensity after 725 years. The paint surface shows no flaking, no blistering, no chalking. The paint has chemically bonded with the wall substrate at the molecular level. It's not a coating applied to the wall, it's part of the wall, integrated into the crystalline structure of the plaster during the curing process. Modern restoration scientists, examining these frescoes, using electron microscopy and chemical analysis, discovered something remarkable. The pigments are more firmly bound to the substrate now than when originally painted. The plaster's carbonation process, converting calcium hydroxide to calcium carbonate, has continued for 7 centuries, progressively locking the pigments deeper into the crystalline matrix. The paint has improved with age. Modern paint reaches peak performance within days of application, then begins a slow degradation that never reverses. Fresco improves for centuries, becoming more permanent as the substrate continues curing. Chapter 2. The plaster that becomes stone. Fresco painting. True fresco, or buon fresco, is painted onto wet lime plaster. The technique demands perfect timing and irreversible commitment. Once you start painting a section, you must complete it before the plaster dries. There are no corrections, no overpainting. The chemistry is unforgiving. The plaster begins as calcium hydroxide mixed with sand and water, spread onto a wall in layers. The surface layer, the intonaco, is applied in sections called giornate, Italian for day's work. This final layer remains workable for 6 to 12 hours, depending on humidity and temperature. During this window, the painter applies pigments mixed with pure water, no binder, no medium, just pigment and water. The pigment particles settle into the wet plaster surface. As the plaster cures, calcium hydroxide reacts with atmospheric carbon dioxide, slowly converting to calcium carbonate limestone. This carbonation process begins at the surface and proceeds inward over months and years. As carbonation occurs, calcium carbonate crystals grow throughout the plaster matrix, incorporating pigment particles into the crystalline structure. The pigments become trapped in stone, literally. They're not sitting on the surface held by binder, they're embedded in calcite crystal lattice. This integration is permanent. You cannot remove fresco pigments without removing the plaster itself. Scraping the surface removes only the outermost layer. The pigments extend into the plaster depth. The Istituto Superiore per la Conservazione ed il Restauro in Rome conducted detailed analysis of fresco cross-sections, cutting microscopic samples from damaged areas of various frescoes. Their microscopy revealed pigment particles embedded 200 to 500 micrometers into the plaster, far deeper than the penetration of any modern paint. The carbonation process had created mineral encapsulation of the pigments. The particles were no longer organic colorants on an inorganic substrate, they were inorganic inclusions in a mineral matrix. The paint had become stone. This explains the permanence. Stone doesn't fade, it's chemically stable across geological timescales. Pigments embedded in stone inherit that stability. Chapter 3. The pigment that costs kingdoms. Medieval painters had access to specific pigments, earth colors, minerals, and a few precious materials. Each pigment had distinct properties, costs, and permanence. Understanding which pigments were used, where, reveals sophisticated knowledge of material chemistry. Earth pigments, ochres, umbers, siennas were cheap and permanent. These are iron oxide minerals, among the most stable compounds known. Yellow ochre is hydrated iron oxide. Red ochre is anhydrous iron oxide. Burnt umber is manganese dioxide with iron oxides. These pigments are essentially rust and manganese ore materials that don't degrade chemically under normal conditions. Medieval painters used earth pigments for backgrounds, shadows, and base layers. The colors were muted browns, tans, yellow browns, red browns. Not spectacular, but absolutely permanent. Frescoes, 800 years old, show earth pigments essentially unchanged from their original appearance. At the opposite extreme was ultramarine blue made from lapis lazuli, a semi-precious stone imported from Afghanistan. The stone had to be crushed, purified through elaborate washing processes to separate the blue lazurite mineral from contaminating calcite and pyrite, then ground to specific particle size. The process was labor-intensive and wasteful typically. 100 grams of lapis lazuli yielded 20 to 30 grams of pure ultramarine pigment. The cost was extraordinary. In 1,390 seconds, Florence, ultramarine cost 8 to 12 florins per ounce, more than gold, which cost 3 to 4 florins per ounce. Using ultramarine blue in a fresco was statement of wealth and devotion. It was reserved for the most important elements. The Virgin Mary's robes, heaven. Important symbols. The painter, Cennino Cennini, writing in 1400, called ultramarine a color illustrious, beautiful, and most perfect beyond all other colors. But ultramarine's importance wasn't just aesthetic, it was also permanent. Lazurite is sodium, calcium, aluminum silicate with sulfur, a complex mineral that's extraordinarily stable. Ultramarine doesn't fade, doesn't darken, doesn't change chemically. Frescoes, painted with ultramarine in 1300, remain as intensely blue as the day they were painted. Modern synthetic ultramarine, developed in 1826, has identical chemistry and identical permanence. It costs $15 per kilogram instead of more than gold, but it performs identically to the medieval pigment. This is rare. Most modern synthetic pigments are chemically different from their mineral counterparts. Chapter 4. The red that turns black. Not all medieval pigments were permanent. Some degraded dramatically, teaching painters through catastrophic failure which materials to avoid. Vermilion mercuric sulfide, a brilliant red, was expensive but common in medieval painting. It produced intense scarlet color, warmer and brighter than red ochre. But vermilion has a fatal flaw. Under certain conditions, it converts to metacinnabar, a black form of mercuric sulfide. The transformation is triggered by light, humidity, and especially chloride ions from salt exposure. Coastal frescoes painted with vermilion often show the characteristic degradation areas that should be red have turned brown-black. The Ghent altarpiece, painted by Jan van Eyck in 1432, has suffered vermilion darkening in multiple panels. The robes that were once brilliant red are now muddy brown. Chemical analysis confirmed the cause. Metacinnabar formation. Medieval painters knew vermilion was risky, but used it anyway because alternatives were worse. Red ochre was duller, madder lake was fugitive. They accepted the risk for the color. Another problematic red was minium red lead tetroxide. This produced orange-red color and was relatively cheap. But lead compounds are chemically reactive. In the presence of sulfur-containing pollutants, which increased dramatically after industrialization, minium converts to black lead sulfide. Frescoes, painted with minium in polluted urban environments, show characteristic blackening. The pigment has reacted with atmospheric pollution and transformed into different compound. The lessons were learned through observation. Painters who used vermilion or minium extensively saw their work darken over decades. Painters who used madder lake saw colors fade. Painters who used earth pigments and ultramarine saw their work remain unchanged. This knowledge accumulated across generations by the Renaissance. Treatises on painting explicitly warned about fugitive pigments and recommended alternatives. The empirical testing ground was actual frescoes, and the testing period was centuries. Modern paint chemistry accelerates this testing through laboratory exposure. But the principle remains. Only empirical long-term testing reveals actual permanence. Chapter 5. The lime that drinks carbon. The chemistry of fresco is carbonation, the conversion of calcium hydroxide to calcium carbonate through reaction with atmospheric carbon dioxide. This reaction is why fresco works and why it's permanent. Calcium hydroxide slaked lime is alkaline, with pH around 12.4. This extreme alkalinity creates a hostile environment for organic growth. Bacteria, fungi, and algae cannot survive on fresh lime plaster. As the plaster cures and carbonation proceeds, pH gradually drops toward neutral. But the process is slow, taking months to years for complete carbonation, depending on plaster thickness and environmental conditions. During the early months, the high alkalinity protects the fresco from biological colonization. This is critical. If bacteria or fungi colonize the surface before carbonation is complete, they can interfere with crystal formation and create weak spots. Medieval painters knew that newly painted frescoes needed protection from moisture and contamination during the critical early months. Covering frescoes with cloths, limiting access, maintaining dry conditions, these practices protected the curing process. The carbonation reaction is KOH2 plus CO2, KaCO, 3 plus H2O. Calcium hydroxide plus carbon dioxide yields calcium carbonate plus water. The reaction is exothermic. It releases heat. It's also irreversible under normal atmospheric conditions once formed. Calcium carbonate doesn't spontaneously revert to calcium hydroxide. The mineral permanence comes from this irreversibility. The Centro per la Conservazione ed il Restauro dei Beni Culturali in Florence conducted decades-long studies of fresco carbonation, using pH measurement and X-ray diffraction to track the conversion process. Their findings showed that surface carbonation is essentially complete within 3 to 6 months for typical intonaco thickness of 5 to 8 millimeters. But deep carbonation, complete conversion throughout the plaster thickness, continues for 10 to 20 years in thick plasters. Some medieval plasters, analyzed 600 to 700 years after application, still showed trace calcium hydroxide in their deepest layers. The material was still curing, still converting to stone, still improving. This extended curing creates progressively stronger substrate. As carbonation proceeds inward, the calcite crystal network becomes more interconnected, the structure denser, the material harder. Fresco on fully carbonated plaster is more durable than fresco on partially carbonated plaster. Medieval frescoes have had centuries for complete carbonation. Modern frescoes are judged within years, before the substrate has reached final strength. Chapter 6. The water that carries color. Fresco pigments are applied with pure water. No oil, no egg, no gum. Just pigment powder mixed with water to create thin suspension. This seems impossibly simple, but it's the key to permanence. Oil paint uses linseed oil as binder. The oil oxidizes and polymerizes, creating a film that holds pigments together. This film is vulnerable. It cracks with temperature changes, darkens with age, becomes brittle under UV exposure. The binder is the weak link, failing before the pigments degrade. Egg tempera uses egg yolk as binder. The protein and fat create a different film with different aging characteristics, but still an organic binder subject to environmental degradation. Watercolor uses gum arabic as binder again, an organic material that degrades over time. Fresco has no organic binder. The binder is calcium carbonate mineral. Permanent. Formed in situ through carbonation, the pigment particles are suspended in water purely for application convenience. As the water evaporates and carbonation proceeds, the pigments become mechanically trapped and chemically integrated with the crystalline matrix. There's nothing to degrade except the pigments themselves, and mineral pigments are extraordinarily stable. This purity is why fresco is permanent. There are no organic materials aging poorly, no binders yellowing or cracking, no media darkening. Just minerals in a mineral matrix, stone within stone. But this purity creates constraints. Only certain pigments work in fresco. They must be alkaline stable. The pH 12+ environment of fresh lime destroys some pigments. They must be mineral-based. Organic pigments often fade under the alkalinity. They must have appropriate particle size, too fine, and they're carried too deep into the plaster, too coarse, and they don't penetrate adequately. Medieval painters had palette of perhaps 15 to 20 fresco-suitable pigments. Oil painters had 40 to 50 pigments available. The limitation forced simplified palettes, but it ensured permanence. Every pigment used in fresco was tested across centuries and proven durable. No experimentation with questionable materials, no fugitive colors, no organic lakes that would fade. The constraints created discipline that preserved the work. Chapter 7. The giornata that defines rhythm. Fresco must be painted in sections giornate because the plaster remains workable for only hours. This constraint shapes composition and reveals working methods. Look closely at frescoes, and you can see the giornata boundaries, slight lines where one day's plaster meets the next. Analyzing these boundaries reveals how the artist worked, which sections were painted first, how the composition was planned, how the team divided labor. Large frescoes required multiple painters working simultaneously. Giotto's frescoes in the Scrovegni Chapel, painted 1,303 to 1,305, show systematic working methods. The backgrounds were painted first, with large giornate covering sky or architectural elements. Then figures were added in smaller giornate, sometimes with one giornate per major figure. The faces were saved for last, painted in tiny giornate, allowing the master maximum time to complete critical details. This working sequence required detailed planning. The master created full-scale cartoons, drawings showing the complete composition. These were transferred to the wall through pouncing, pricking holes along the cartoon's lines and dabbing charcoal through the holes, leaving dotted outlines on the fresh plaster. Some cartoons were incised, pressed into the wet plaster with a stylus, leaving grooves marking the design. These underdrawings guided the painter during the brief window of workability. The time pressure created urgency that shaped the aesthetic. Fresco brushwork is decisive. Hesitant strokes are visible. Corrections impossible. The artist must work confidently, each stroke contributing to the final image without possibility of revision. This creates visual energy. Fresco paintings have immediacy that carefully worked oil paintings lack. The medium demands confidence, and that confidence is visible in every brushstroke. Modern painters working in fresco describe the psychological pressure, knowing that once the plaster is mixed and applied, you have perhaps 8 hours to complete the section. No breaks, no corrections, just focused intensity until the giornata is finished or ruined. The constraint is creatively generative. It eliminates indecision and overthinking, forcing commitment that produces vigorous work. Chapter 8. the decay that doesn't happen. Medieval frescoes survive in remarkable condition considering their age and exposure. Many have endured 600 to 800 years of temperature fluctuations, humidity changes, pollution, and general neglect. Yet they remain substantially intact. The durability comes from mineral stability. Calcium carbonate doesn't decompose at normal temperatures. The mineral pigments don't degrade chemically. There are no organic materials to rot. The paint is stone, and stone is permanent on human timescales. The primary threat to frescoes isn't internal degradation, it's external damage. Water infiltration can cause efflorescent salts migrating through the plaster and crystallizing on the surface, lifting paint away from the substrate. This is mechanical damage, not chemical degradation. Structural movement can cause cracking, the plaster cracks, and the paint layer cracks with it. Again, mechanical damage. Biological colonization, algae, lichen, bacteria can occur on frescoes in humid environments, but this affects the surface, not the underlying paint structure. The most significant threat is actually restoration and conservation. Well-meaning but misguided interventions have damaged more frescoes than natural aging. In the 1800s, conservators often refreshed faded frescoes by painting over them with oil paints or applying varnishes. These treatments trapped moisture, accelerated deterioration, and obscured the original surfaces. Removing these later additions without damaging the original fresco is extremely difficult. The Brancacci Chapel frescoes in Florence underwent restoration in 1,980 seconds that required removing centuries of accumulated dirt, candle soot, and later overpaint. The cleaned frescoes revealed colors and details that hadn't been visible for 400 years. The paintings weren't degraded, they were just obscured by contamination. Once cleaned, the original surfaces were pristine. Modern conservation philosophy has changed from restore to preserve, removing harmful contamination but leaving the original surfaces untouched, even if aged or damaged. This approach respects the material integrity and allows the fresco's natural permanence to continue functioning. The Courtauld Institute of Art's wall painting conservation program studied dozens of medieval frescoes, documenting their condition and aging patterns. Their findings consistently showed that properly executed fresco paintings on sound plaster remain stable indefinitely. The technique works. The material is permanent. The only failures are from improper execution, plaster applied to damp walls, inappropriate pigments, contaminated materials, or from external damage like water infiltration or structural failure. These are execution or maintenance failures, not material failures. Chapter 9. The modern paint that dies. Contemporary paint is fundamentally different from fresco. Modern paint is organic polymer containing pigment particles, applied as liquid that dries to solid film. The film isn't part of the substrate, it's a coating on the substrate, held by adhesion forces. This coating is vulnerable to every environmental stress. UV radiation breaks polymer bonds, causing chalking. The paint turns to powder. Water penetrates the coating, causing swelling and delamination. Temperature cycling creates expansion and contraction, eventually cracking the film. Biological growth mildew, algae colonizes organic polymers, especially in humid climates. The failure mechanisms are numerous and inevitable. Exterior latex paint. The most common modern coating is acrylic polymer with pigments and additives. The polymer provides color retention and flexibility. But acrylic degrades under UV exposure. The polymer chains break, losing their binding ability. Pigments remain, but they're no longer held together. The surface chalks and erodes. Paint manufacturers know this. They formulate exterior paints with UV stabilizers, chemicals that absorb UV radiation before it can break polymer bonds. But the stabilizers are consumed by this process. They're sacrificial protectors that eventually deplete. Once stabilizers are exhausted, degradation accelerates. Paint industry testing standards measure time to failure, not permanence. A paint might be rated for 10-year durability, meaning it will maintain acceptable appearance for 10 years before requiring repainting. This is planned obsolescence embedded in material specifications. The paint is designed to last exactly long enough to satisfy consumers, but not so long that it reduces replacement demand. Consumer Reports tested exterior paints in 2018, applying them to test panels and exposing them to accelerated weathering. The best-performing paints showed chalking after 8 to 10 years equivalent exposure. No paint tested exceeded 12 years without significant degradation. The testing confirmed what the industry already knew. Modern paint is temporary. Compare this to fresco, where permanence is measured in centuries. The material difference is fundamental organic polymers versus mineral crystallization. One degrades inevitably. The other is stable indefinitely. Chapter 10. The Economics of Repainting. The paint industry generates $80+ billion annually in global sales. That revenue depends on continuous repainting. If paint lasted 50 years instead of 10, the industry would shrink to 20% of current size. This creates perverse incentive. The industry profits from inferior products requiring frequent replacement. Paint manufacturers could produce more durable coatings, advanced polymer formulations, ceramic-modified coatings, mineral-based paints that last 20 to 30 years exist. But they're not mass-marketed because they would undermine the replacement cycle that generates revenue. The industry instead focuses on marginal improvements, paint that lasts 12 years instead of 10, while maintaining the fundamental need for frequent repainting. Homeowners bear the cost. The average American house requires exterior repainting every 8 to 12 years at a cost of $3,000, $8,000, depending on size. Over 50 years of homeownership, expect to repaint 4 to 6 times, totaling $15,000, $40,000. Interior repainting occurs even more frequently, every 5 to 7 years, at similar cost per cycle. Total lifetime painting costs for a typical house approach $100,000. These are maintenance costs that shouldn't exist. Buildings shouldn't require continuous repainting to prevent deterioration. Medieval buildings didn't fresco protected walls for centuries. Stone and lime plaster buildings didn't need paint at all. The materials were inherently weather-resistant. We've created building systems that require continuous chemical coating to prevent deterioration, then normalized the coating replacement as necessary maintenance. It's not necessary, it's profitable. For the paint industry, the economics explain why fresco isn't promoted despite its superiority. True fresco requires skilled application, extended drying time, and specific substrate preparation. It can't be sold in retail stores for DIY application. Most importantly, it never needs repainting. These characteristics make fresco unmarketable to an industry built on selling replacement coatings. The superior technology is economically unviable. Chapter 11. The Artist Who Remembers. In a studio in Tuscany, a fresco painter named Lucia Cardinali teaches a dying art. She learned from master Leonetto Tintori, who restored frescoes throughout Italy in the mid-1900s and trained a small group of apprentices in traditional techniques. Lucia is 58, and she's teaching perhaps 20 serious students worldwide, people committed to learning fresco properly, understanding the chemistry and craft. She's demonstrating plaster mixing. 3 parts aged lime putty to 1 part clean river sand, mixed with water to workable consistency. The lime putty has been aging for 2 years. Fresh lime doesn't work for fresco, as it contains impurities and hasn't fully hydrated. The sand is washed to remove clay and organic material that would weaken the plaster. She applies the intonico in sections, smoothing it with a trowel, checking the surface for proper texture. Too smooth, and pigments don't penetrate adequately. Too rough, and the surface is difficult to paint. The texture must be slightly sandy but cohesive. She begins painting while the plaster is still damp, mixing dry pigments with water on a palette. The technique is watercolor-like, but faster the plaster absorbs water rapidly, so the paint must be applied with decisive strokes. She works confidently, building the image through layered washes and precise details. 4 hours into the session, She tests the plaster by touching it. The surface is drying. She has perhaps 1 more hour of workability. She accelerates, completing the figure's face and final details before the plaster becomes too dry to accept paint. The giornata is finished. Tomorrow, she'll apply adjacent plaster sections and continue the composition. Lucia explains that she completes perhaps 3 major frescoes per year, large works, taking months of careful execution. She earns enough to live modestly, supporting herself through commissions from churches, museums, creating replica frescoes for educational display, and wealthy individuals wanting durable artwork. The market is tiny. Her apprentices, even if fully trained, will struggle to make living from fresco alone. Most will teach art, work in restoration, or paint in other media, while occasionally working in fresco. The craft survives through passionate individuals accepting economic marginality to preserve knowledge they believe is valuable. When Lucia retires in 10 to 15 years, her students will carry the knowledge forward. But how many will still be practicing? How many will train the next generation? The continuity is uncertain. Chapter 12. The science that validates antiquity. Modern conservation science has extensively studied fresco chemistry, validating medieval techniques and revealing their sophistication. The Getty Conservation Institute conducted decade-long research into fresco materials and deterioration, analyzing hundreds of medieval frescoes and testing various pigments and plaster formulations. Their findings confirmed that traditional methods aged lime putty, clean sand, mineral pigments, painting on fresh plaster produce optimal results. Modern shortcuts, commercial hydrated lime, unwashed sand, organic pigments, all produce inferior frescoes with reduced durability. The research identified why aged lime putty is critical. Fresh lime contains unhydrated calcium oxide particles that hydrate slowly over months or years, causing expansion and cracking. Aged lime has completed this hydration, creating stable material. Medieval practice of aging lime for years wasn't superstition. It was materials engineering, ensuring proper chemistry. The study of pigment behavior in alkaline environment revealed why medieval painters' palettes were limited. Organic pigments, madder lake, indigo, saffron, are destroyed by alkalinity, fading or discoloring rapidly in fresh lime plaster. Only alkaline stable mineral pigments, earth colors, ultramarine, lead white survive. Medieval painters learned this through trial and error, watching organic colors fail and mineral colors persist. The carbonation process has been studied in detail using isotopic analysis and crystallography. Research at the University of Bologna's Department of Cultural Heritage showed that carbonation doesn't just convert calcium hydroxide to calcium carbonate. It creates specific calcite crystal structures that interlock with pigment particles. The crystal growth occurs around and through pigment clusters, mechanically locking them into the plaster matrix. This explains why fresco pigments are so permanent. They're not just sitting in calcite, they're surrounded by it, trapped in three-dimensional crystal lattice. Modern fresco practitioners using these scientifically validated methods report success. But they face challenges medieval painters didn't encounter: air pollution, which can interfere with carbonation; climate control in buildings, which may slow drying; and impatience from clients accustomed to fast-drying modern paints. Medieval frescoes cured in churches that were temperature-stable, naturally ventilated, and protected from direct weather. Modern frescoes must adapt to HVAC systems, sealed buildings, and different environmental conditions. Some adaptations work, others compromise durability. The tension between traditional methods and modern conditions is an ongoing challenge for contemporary fresco painters. Chapter 13. The building that rejects paint. Modern construction methods often create substrates unsuitable for fresco: concrete block, gypsum drywall, cement, stucco. These materials have different chemistry than lime plaster. Fresco requires lime-based substrate for proper bonding and carbonation. Painting fresco on gypsum or cement produces poor results. The chemistry doesn't support proper pigment integration. This means fresco is practical only on buildings constructed with traditional materials, lime plaster on brick or stone, or on buildings where appropriate substrate can be added. Some architects designing contemporary buildings incorporate fresco, specifying lime plaster surfaces specifically for painted decoration. These projects are rare, perhaps a few dozen worldwide annually, but they demonstrate fresco's viability in modern contexts. The Cathedral of Our Lady of the Angels in Los Angeles, completed 2002, includes fresco paintings by John Giuliani. The architect specified lime plaster surfaces on concrete structure, creating appropriate substrate for fresco work. The paintings have now been in place 20+ years, showing no degradation. The experiment is succeeding. More commonly, traditional buildings with lime plaster substrates are available for fresco work during restoration or renovation. Medieval churches, historic buildings, and preserved structures often retain original lime plaster or can have it replaced during conservation. This creates opportunities for fresco painters, though the work is specialized and limited in scope. The fundamental problem is that modern building practice has eliminated the substrate fresco requires. We build with materials optimized for speed, economy, and structural performance. Concrete, steel, gypsum, cement. These materials aren't compatible with fresco chemistry. Unless architecture returns to lime-based plasters, unlikely given construction economics, fresco will remain niche technique suitable only for specialized projects. The superior painting technology survives only where compatible building technology exists. Chapter 14. The restoration that reveals. When conservators clean centuries of accumulated dirt, soot, and discolored varnish from frescoes, they often reveal startling color intensity. The paintings aren't faded, they're just obscured. The Sistine Chapel ceiling restoration, conducted 1980 to 1994, removed centuries of contamination from Michelangelo's frescoes. Art historians had assumed the frescoes were painted in muted, somber tones. The cleaned surfaces revealed brilliant, saturated colors, vivid blues, intense reds, bright yellows. The paintings weren't dark and somber, they'd been darkened by centuries of candle, soot, and poorly applied varnishes. The revelation sparked controversy. Some critics argued the cleaning was too aggressive, removing original material along with contamination. Others insisted the vibrant colors were authentic and prior restorations had darkened the frescoes. The debate revealed disagreement about how frescoes should look, whether the aged, darkened appearance was authentic character or obscuring contamination. Chemical analysis ultimately confirmed that the bright colors were original. The dark appearance was entirely due to surface contamination. Michelangelo had painted with intense colors, and those colors remained intact under the grime. Similar discoveries occurred with other fresco cycles. The Brancacci Chapel frescoes, when cleaned, revealed delicate modeling and subtle color relationships invisible under contamination. Giotto's frescoes in Padua, when restored, showed detailed underdrawing and careful color planning. The frescoes weren't crude early Renaissance work, they were sophisticated paintings obscured by later damage and dirt. These restorations teach important lesson. Fresco's permanence means the original surface remains intact, even after centuries of neglect. The paint doesn't fade or degrade, it just gets dirty. Once cleaned, the original surface is revealed, often in remarkable condition. Modern paint doesn't work this way. Cleaning doesn't reveal fresh paint underneath because the paint itself has degraded chemically. The faded appearance is actual material failure, not removable contamination. Restoration cannot reverse degradation, it can only slow it. Fresco restoration is primarily cleaning, removing contamination that obscures but doesn't damage the underlying paint. The paint itself needs no restoration because it hasn't deteriorated. Chapter 15. The paint that refuses to die. You cannot buy fresco supplies at hardware stores. But specialty art suppliers carry lime putty, mineral pigments, and sand suitable for fresco. The materials cost perhaps $200 for enough supplies to paint several square meters. The technique is documented in numerous books and online tutorials. The knowledge is accessible, The barriers aren't technical, they're substrate and commitment. Fresco requires lime plaster substrate, which most modern buildings lack. Creating appropriate substrate means applying lime plaster to existing walls possible, but requiring plastering skills. And fresco demands commitment. Once you mix plaster and begin painting, you must finish that section before it dries. There's no pausing and returning later. For these reasons, fresco remains specialized technique. But its permanence makes it worthy of consideration for specific applications. Murals in public buildings where long-term durability matters, artwork intended as permanent cultural legacy, or restoration of historic frescoes requiring matching technique. The paint that defies time is still possible. The chemistry works. The materials are available. What's missing is cultural willingness to value permanence over convenience, to accept constraints that produce superior results, to build with materials that support rather than prevent durable painted surfaces. Medieval painters created work that has survived 700 years and will likely survive 700 more. We create work that requires repainting every decade and accept this as normal. The difference isn't technology. We have better chemistry, better tools, better understanding. The difference is priorities. Medieval painters built for eternity because their culture valued permanence. We build for the present because our economy values consumption. The fresco is waiting in scattered studios, in old techniques, in walls painted centuries ago that still glow with color. It's showing us that permanence is possible, that materials can outlast empires, that human craft can create work surviving across civilizations. The paint refuses to die. The question is whether we're worthy of using it.